Okay, now we will start on with the next example of the branch and bound. As I told you in the previous class, branch and bound, it is the enhancement of backtracking. It is applicable to the optimization. It will be computing the bounded value. Now, when you are computing the bounded value, there will be a function used based on the objective function for all the descendants of the node. We are going to extend the partial solution. So here it will be using the bounded value for ruling out certain nodes as it is considered to be the non-promising nodes. And if at all a node's bound is not better than the best solution also, we will be considering it as non-promising here. And we will be guiding the search through the state space. So here, when you go for the branch and bound, it needs two items, additional values, which is for each and every node we are calculating the bounded value, and we will be representing it with the help of the objective function, and we will be seeing what are the components are. So the best value seen so far will be considered as the optimal solution. So here, when you terminate a node, the termination of a node takes place at three particular instances. One is if the node's value is not better than the other node value, or if it is violating the constraints, if it is not a feasible node. Feasible node will be always satisfying the constraints. So based on the feasibility also, you will be saying it. When you compare the values of the objective function also, we will be choosing the better one. So whatever we have got a latter one, that will be replaced for the former. Okay, so these are the three reasons where usually we terminate a search path. So now we are going to the next example. The previous example which was seen here is your assignment problem, which is a minimization problem. Now we move on to the next example, that is your knapsack problem. So here the knapsack problem is nothing but it is a maximization problem. So you can see here, when you say it as a knapsack problem, you should first know what is this problem all about. So for a knapsack problem, we have already seen in our brute force approach, as well as we have also seen in our dynamic programming method that we can solve in two different ways the knapsack problem. Now the third way which we are going to see the knapsack problem is the branch and bound technique. So here, when you say it as the branch and bound technique, we will be saying it as for the branch and bound, you will be given with a knapsack problem which says that there are n items. Each item will be having its own weight as well as value, and there will be a knapsack also. So the knapsack capacity, maximum capacity will also be given. You need to find out the most valuable subset of the items which will fit into your knapsack. So for that, what we need to do is, suppose if there are 5 different items, you may not be able to fit into the knapsack with all the 5 items. So we will be seeing which items, if you choose, we will give you a most profitable one. We always, when you go with a, for example, when we were seeing dynamic programming also, we have seen the example of considering a courier service where there are various packets for each one will be having its own weight and its value. So here what we will be seeing is, for each one we will be seeing what is the weight and the value. So we will be choosing the one which gives you a most profitable one. So here we need to arrange the items in the descending order by giving their own weight as well as the values. So the ratio has to be determined. Then you can say that the first item gives you the best payoff. For example, you consider the courier service where you have getting different parcels from different customers. So when you get 5 different packets, you need to put it in a container where the container will take only 100 tons a maximum. So you will be measuring each packets. You will be choosing the packets. You cannot put more than 100 tons into that container. But obviously you will be seeing what is the profit for each parcel or each packet. So based on that, you will be considering one which gives you a maximum profit. So similarly here the knapsack problem which is given based on the branch and bound is, you need to get a best payoff per weight unit. So what we will be doing is, we will be arranging the objects in such a way that you find out the ratio of each and everything. Okay, where you will be saying it as it is value divided by weight. For each item you have its own value and its weight. So please find out the ratio, and once if you find out the ratio, put it in the decreasing order. Okay, the maximum, whenever you do a business, you are aiming for a maximum profit. So why don't we consider it in a descending order? So we will be considering it in a descending order where you take the best payoff. So you put it in the decreasing order. The first thing is, you need to find out the ratio, and based on the ratio we are putting it in the decreasing order of their weight. So this is how we go with the flow for arranging the objects in such a way that each and every object, whenever you take, we will be considering what is its ratio and we will be arranging it. So here it is going to be represented again. You have seen our assignment problem. In the assignment problem, based on the number of choices, each level the children will be varying. With the 4 children, 3 children, 2 children, etc. But here we are again going to represent it as a binary tree, where you are saying that your left child will be including the item and the right child will be excluding the item. And since it is a maximization problem, we need to calculate the bounded value, and here the bounded value will be a upper bound value, because you are going for a maximum value. So we need to find out the upper bound value by using a formula which says that what is the current value, what is the remaining capacity, and what is the payoff per unit weight for the next item. So the formula given here is, supposing if we are given with 4 items, here we are given with 4 items, correspondingly its weight as well as value is given. So what we do is, we need to find out the value plus the what is the remaining capacity, that is the maximum capacity minus the current what is the current items weight. So remaining capacity into multiplying with the ratio of the next item. So first find out value by weight and arrange the items in such a way that the highest ratio will be the first one. So you are putting it in the decreasing order of the ratio. V1 divided by W1 should be greater than or equal to V2 divided by W2, etc. up to Vn divided by Wn. So what is the maximum knapsack capacity given? 4 items are given. All items it's given with its weight as well as value, and you are given with the knapsack capacity also, which is 10. So now we are going to solve the problem where it says that we will be calculating the upper bound value by using this formula. So the formula says that for you have to calculate first for node 0, and we know obviously for a root node we will not consider any element, so the weight will be 0, value will be 0. Now, how to consider the upper bound value? For this node 0, if you take, it's given as node 0 is, what is the value? Value is 0. What is the remaining capacity? Remaining capacity is total capacity. Total capacity is 10 minus the weight of this particular node. Here in the root node, we are not considering any items. So the weight and the value will be 0 respectively. So it's 10 minus 0 into the ratio of the next item. What is the ratio of the next item? The ratio of the next item is 10. So we are calculating it as 0 plus 10 minus 0 into 10, which is equal to 100. Clear? So the upper bound value for root node we have calculated, it is 100. Now we will move on to the next one. What is the next one? We need to consider the tree. State space tree has to be further generated by having two children. One is with item 1, without item 1. When you say it as with item 1, what is the first item's weight? Weight is 4. What is the first item's value? Value is 40. So now, what will be your upper bound value? You just calculate it. The upper bound value is nothing but we are saying that the upper bound value has to be calculated by taking W as 4, V as 40, upper bound is value is 40. 40 plus, what is the total capacity? Total capacity is 10 minus the current node, what is the weight? It is 4. So 10 minus 4, that is the remaining capacity into ratio of next item. Now we are in the first item with 1. 1 means with item 1. So we are in the first item. So we see the I plus 1. I plus 1 is, it will be equal to 2. So we are taking it as 6. So 40 plus 10 minus 4 is 6. 6 into 6 is 36. 40 plus 36, you will be getting it as 76. So here you got the value as 76. Clear? Understood? Are you getting it? Now, what will be for the left child? The left child is without item 1. Without item 1, the weight will be 0, the value will be 0 because we are just taking it from the root node. So, now, when you say it as weight as 0, value as 0, what is happening is you are calculating the upper bound with the value 0 plus the remaining capacity. Remaining capacity is maximum capacity is 10 minus the value for weight for this node is 0. So 10 minus 0 into 6. So 10 minus 0 is 10. 10 into 6, 60. 60 plus 0, 60. So the upper bound value for the node number 2 is 60. Getting it? So you have now node number 1 with the 76, node number 2 with 60. Among this, which you feel as the most promising one? Both are promising nodes because they are satisfying our constraints. The constraints are not violated here. So without violating the constraints, we have come up with the two choices. Node 1, node 2. Node 1 is with item 1 and node 2 is without item 1, where you are getting a value as 76 and 60. So here we will say that the 76 value 76 is the value 76 is the most promising one, and we will be moving further with that. So when you go with that, what will be your next level? Next level will be with 2, without 2. So you need to calculate for node number 3 and node number 4. Now, when you say it as node number 3, if you see, what is the weight of the previous one? It is 4. Now, including the next item, what is the next item weight? The next item weight is 7. 4 plus 7, what is the weight? Total weight 11. Can we include the second item into the knapsack? Is it possible? No. Why? Because the maximum capacity is 10, but here we have already got it as 11. 4 plus 7 is 11, which is not at all possible. Okay. So this is not satisfying the constraint, so we need not generate it further, or we need not calculate even the upper bound value. Now we will go without 2. Without 2 means it indicates that at present you have only the first item in the knapsack. So whose weight is, just to take the values from the parent node. Weight is 4, value is 40. Okay, but you are now your I value is 2, that is you are in second level. So the next ratio to be considered is for the third item. So here we are going to calculate the value. So when you are calculating the value, what is the value now? The value will be, you are saying it as node 4 is calculated with weight 4, value 40. So your upper bound is 40 plus what is the remaining capacity? The maximum capacity is 10. Current item weight is 4. So remaining capacity is 10 minus 4. It is 6 into the ratio of the next item. You are in your I value is equal to 2. So I plus 1 is obviously it is 3. So the third ratio is 5. So 5. So 10 minus 4 is 6. 6 into 5, 30. 30 plus 40, you are getting it as 70. So here we got it as 70. Clear? So now, if you consider in node number 2, we have got a value as 60. Node number 3, it is not feasible at all. Node number having 70. Among 60 and 70, which is the most promising one? The most promising one is node number 4, whose value is 70. So next we will move on to 4, node number 4. Now when you say it as node number 4, we are going with 2 children, with 3, without 3. We get 2 nodes, node number 5, node number 6. Node number 5, if you see, we are going to include the third item. So in the parent node, already what is its weight? Weight is 4. So 4 plus, what is the weight of the third item? It is 5. So 4 plus 5 is, we have got it as 9. What is the value? Already in the parent node, the value is 40. What is the third item's value? Third item's value is 25. So 40 plus 25, it is 65. So here we are having it as weight equal to 9 and value equal to 65. So now you need to calculate the upper bound. How will you calculate the upper bound for node number 5? Node number 5, the upper bound is calculated as weight is 9, value is 65. So your upper bound is equal to, we have the formula. Formula is value plus the remaining capacity. What is remaining capacity? Total capacity is 10 minus the current capacity is 9. So 10 minus 9 into, now we are in the third level. So what will be the ratio for the next item? The next item's ratio is 4. So into 4. 10 minus 9 is 1. 1 into 4, 4. 4 plus 65, you are getting it as 69. So node number 5, you are getting the value as 69. Now, that is over. So now we will come to the next one. The next one, if you see, it is saying without 3. Without 3 means you are not going to include the item 3. So when you are not going to include the item 3, what will be the weight? Weight is the parent node's weight, which is 4. Value is 40. It is weight and value is retained as it is. Now we need to calculate the upper bound. So the upper bound is calculated in such a way that the value 40 plus remaining capacity 10 minus 4. 4 because the current weight is only 4. So 4 into, what is the ratio of the next item, it is 4. So 10 minus 4 into 4. So 10 minus 4 is 6. 6 into 4, 24. 24 plus 40, it is 64. Getting it? So here, node number 5 and 6. Among 5 and 6, which is the most promising? Most promising one is node number 5. Node number 5, we have the value as 69. So we are moving ahead with 69. Now what will be the next level? Can you just guess it? We have seen with 1, without 1, with item 2, without item 2, with item 3, without item 3. So obviously the next level will be with item 4 and without item 4. With item 4, already in the parent node, what is the weight? The total weight already it has become 9 in the knapsack. This is what it is being chosen. So in the knapsack is already holding some items and its total weight is 9. What is the weight of the current one? It is weight of item 4 is 3. 3 plus 9 is 12. Whether it will be satisfying your constraint? No. What is your constraint says? It should fit into your knapsack. So it is exceeding the knapsack capacity. So we will not be considering it as a feasible one. So we will move with without 4. When you say it as without 4, we are not going to include the item 4. So we need not bother its weight. So weight and value will be whatever it's there in your parent. The weight will be 9, value will be 65. So you need to calculate the upper bound. So now what will be the upper bound value? So the upper bound value is calculated as node number 8 because 7 is not feasible. So node number 8 is going to be calculated with 8, 9, value 65. So your upper bound value is 65, that is your value, plus the remaining capacity. Remaining capacity is 10 minus 9 into. Now what is this? That is nothing but it is Vi plus 1 divided by Wi plus 1. So what is this 0 indicate? 0 indicates that already we are in the 4th item. Now we are in the 4th item. There are no more items. So the ratio of the next item, if you see this, in this formula, if you see this part, the ratio of the next item is, there are no more items, so the value is 0. So 10 minus 9 is 1. 1 into 0, 0. 0 plus 65, the value is 65. Getting it? So node number 7 is not feasible. Node number 8, the value is 65. Okay. Now we need to compare it with the values which we have discarded. So for that we will move on to this level where at this particular point we are comparing 70 with the 60, which is maximum. 70 is maximum. So we have moved further. Now you have 69, you have 64, you have 60. Among this, which is the most promising one? The most promising is the one which is having the value as 69. Now, so 69 is further generated. So among 69, which is the most promising node? The most promising node is you have value as 65. 65 is compared with the 64 and 60. Both are inferior to node 8. So this is considered to be the optimal solution. Now, in this, when you consider it as the optimal solution, so we are saying that the optimal solution is 60. What are the items included? Now, to find out what are the items included, what you need to do? Like same as your sum of subset, we need to start from the root node, traverse this path. When you traverse through this path with item 1, without item 2, with item 3 and without item 4, which means that you have included only 2 items, that is item 1 and item 3, to get a solution as 65. So optimal solution here it is 65. What is the optimal solution? It is 65. What is the items? Items included are item 1 and item 3. Now you just cross check it. Before confirming it, please cross check it. Item 1, item 3, item 1 the value is 40, the value of item 3 is 25. 40 plus 25, 65. What is the weight? Total weight is, here it is 4, here it is 5. 4 plus 5, 9. So is it feasible? Yes, it is feasible. So like that, if you want to cross check, you can just cross check it. And you can find out which will be your optimal solution. Okay. So when you go for the knapsack problem, it is a maximization problem. Now, when you say it as a maximization problem, we are calculating the upper bound value. When you calculate the upper bound value, there will be a function, objective function. The objective function here, it is nothing but it says that you need to find out the value. You need to add it with, first find out what is the remaining capacity, multiply with the ratio of the next item. Whatever product you are getting, you add up with the value, you will be getting the upper bound value. So we have followed the same thing from the beginning, and now you know that the tree consists of only 2 children, the left child and the right child. The left child is the inclusion of the item, and the right child says that the exclusion of the item. When you include the item, you try to add the weight as well as the value. When you exclude the item, you should not add the weight and the value. Whatever is there in the parent node, it will be considered as it is. So now for each node, you need to calculate the upper bound value. So here, for example, we are calculating for node 1 and node 2. Node 1, the value is 76. The node 2, the value is 60. So when you compare 76 with the 60, which is the maximum is 76. So we are going ahead with 76 because it is considered to be the most promising one. The next one, we will be including item 2 and we are excluding item 2. In the left, when you are including the item 2, already in the knapsack we have a item with the weight as 4. So what is the second item's weight? 7. When you include the item, it becomes 4 plus 7, which is 11. It is exceeding the maximum knapsack capacity. So it is considered to be not feasible. So you go with without item 2. Without item 2, whatever is recorded in the parent node for the weight and the value, it will be as the same. Use the formula, calculate the upper bound value. The upper bound value is calculated and you have obtained it as 70. Now, you need to compare 70 with 60, which is maximum, 70 is maximum. So we are again going for further or forward. We are going forward where you are saying that with item 3, without item 3. When you say it as with item 3, you are including the third item. The third item already in our knapsack, the weight is 4. Third item is having a weight as 5. So 4 plus 5, it is 9. Now, already you have a value as 40. The third item's value is 25. So 40 plus 25, it is 65. Calculate the upper bound. Without item 3 indicates that you are not going to include this third item. So whatever is there in the parent node, you take it as it is. Weight is 4 and the value is 40. calculate by using W, V and the ratio of the next item. The ratio of the next item is 4. By using it, calculate for node 5 as well as node 6 the upper bound value. Node 5 and 6, the upper bound values are calculated as 69 and 64. Since both are promising nodes, you consider the one which is giving you the most promising. Most promising is 69, so we are going further. Now, already the weight is 9, so if you include the next item, the weight becomes 12. It is not feasible. So, we are going with weight value, calculate the upper bound without item 4. Without item 4 means node 3 is not added. So you will be getting whatever it's there in the parent node as it is. So it is 9 only. Value is also as retained as it is. Now you are calculating the upper bound value. But note that since you are in the last item, the ratio for the next item, we have taken the ratio for the next item is going to be 0. Why? Because there is no more nodes to be taken. So, no more items to be considered. So, your upper bound is calculated and you are getting a value as 65. Now, you need to find out which is the best value. Best one. So, consider node number 8. Node 7 is not feasible, so it is a dead end. Node number 3 is also a dead end, but there are some promising nodes. So compare with the promising nodes. When you compare it, it is 64, 60. It is less, inferior to node 8. So this is considered to be the optimal solution. But suppose your value of node number 6 is 66 or something that is greater than 65, then you need to consider this. You need to generate this further. Supposing if this value is greater, then you need to consider this also. So whenever you go for the next stage, you are just comparing it with all the nodes which were the promising nodes. But you are going to generate it further only for the most promising nodes. But still, you need to, at any particular level, you need to compare it with the promising nodes value. The non-promising nodes, you just discard it. It is already terminated. Why? Because the constraints are not satisfied. But whereas in the promising nodes, the constraints are satisfied. So you may get a better value. Who knows? Isn't it? When you evaluate only, you will be getting to know. So based on this, we will be getting a solution. So this solution, you need to write it. Okay, draw this tree structure. The entire tree structure has to be drawn. And also you need to say what is your optimal solution, what are the items included for the optimal solution. Finally, you can recheck with your table values. Table values, it shows that 40 plus 25. See, supposing if you take first and second item, 4 plus 7, it is 11. It is not feasible. Supposing if you take 7 plus 3, it is 10. But what is the value? 42 plus 12, it's only 54. 54 is less than 65. So like this, if you want to cross check with your table value manually to confirm whether your solution is correct, that also it can be done. So hope you all have understood this problem. It's very simple problem. All the problems in this chapter are very simple. So once if you understand and if you know, if you remember the formulas is very, very important. If you remember the formulas, this problem can be easily worked out. And it is a maximization problem. So only go with the maximum value. Clear? So I've taken another example. It says that n equal to 4, W equal to 16 with all weight and value for all the 4 items and the maximum capacity is given. Use the formula, calculate and find out value, upper bound value for the root node. Similarly, in the upper bound, for the root node, the weight and value will be 0. So based on that, you calculate all the values. compare the values and get to know what is your optimal solution. So when you get the optimal solution, you just see. For example, here I have given the entire tree structure where you have 154, 144, which is maximum. 154 is maximum. So we have gone further. But when you go for 142, you are calculating 142 with 144, which you feel it as maximum. 144 is maximum. So node number 5 and 6 are generated. But node number 5 and 6 is compared with 4. Which is maximum? 4 is maximum. So we have generated it. Now you are getting two nodes, 7 and 8. 7 is not feasible. You are calculating the value of 8. 8 is compared with 5 and 6, which is maximum. Node number 5 is maximum. So you are generating 9 and 10. So now what are the promising nodes? Node number 8, 9, 10 as well as 6 also. All these are considered to be a live nodes. So compare all the live nodes. Among all the live nodes, this is node number 9 is considered to be the most promising, and you are generating it further to get a solution. Now when you get node number 11 and 12, 11 is not feasible, 12 is feasible. You are calculating the value too. So node number 12 is compared with 8, 10, 6. Among 8, 10 and 6, which is the best one? Best one is 12. So that becomes your optimal solution. Okay. So you can take some problems which is worked out in the exercise, or you can go back to some textbooks where there will be exercise problems, or some question papers, old question papers you can refer where there will be some extra problems. You can please work it out. When you work it out, you will come to know whether you have understood the problem or not. So after working out, if you are held up in some places where you don't know how to proceed further, then you can just please contact me. I will help you to go further, or just tell you whether the your working is correct or not. Okay, where you have gone wrong, everything we will be seeing it once if you do it. So please do a problem and just check. Maybe while teaching, if you just listen, you may feel that this is very easy and you will be just ignoring it. Don't do that. Whenever you have problems, try to work out with the different problems. Okay, when you work it out only, you will come to know whether you are able to complete it, or whether you are stuck up somewhere. If you are stuck up somewhere and if you have any doubts, you can just call me and you can clarify your doubts. So I'm there always to clear your doubts. So please, whenever you feel that you are not able to, you are stuck up somewhere, you are not able to go further, please get in touch with me. We will clear the doubts and then we will be moving further. Okay. So there is one more problem left out for this technique, that is your traveling salesperson problem, that we will be seeing it in the next class. So that's all for today, and I'm winding up this session. Okay, thank you.